Please take your seats so that we can start our third keynote of the day. Well, it's my great pleasure to invite up to the stage Randy Shoup. He's been working at Google and eBay, and he's built big pieces of software. And he's also been somebody who's been working on microsystems for quite a long time, which, if you're honest, doesn't include too many of us. So it's really a treat to have him come up and talk about events and how they're used to coordinate things that are inherently asynchronous. Once you have lots and lots of microservices working at scale, the coordination can become part of the difficulty. So he's going to tell you a lot more about that. I don't want to say any more. But let's welcome Randy.
Great, thank you, Mike. I have to just stop and say, if we're going to talk about architecture, let's take a moment and be impressed by the physical architecture of this building, right? I have said to probably now 10 people here, I find it hard to think of a building that I have seen in my 49 years on this planet that I like more than this. And there's a wonderful story which the woman in front told me, don't all go up at once and ask, but the architect drove on his Harley all around the state and got a feel for what the great things are about Minnesota, and there are so many. But the wood and the water feature and the northern lights, which are supposed to be represented by the windows up there, the granite, all these things are representations of this great state. So anyway, wow, it's such an awesome place to talk about architecture. And if you want to talk about legacy systems, like that, the sound engineer, Marty, was telling me that brick canted archway, that was the original entrance to the stadium, which was on this site, for whatever, 70 years or something. And so he remembers, when that actually was the entranceway and all that kind of stuff. So anyway, admire that as well. Just a stunning building. All right, cool. Let's talk about software architecture. But first, a little bit of background about me, just so you can understand where some of these lessons are coming from. So I'm currently VP of Engineering at Stitch Fix. Who's heard of Stitch Fix? Wow, an excellent, surprising number. I will tell a little bit about Stitch Fix's model. We're a clothing retailer, actually, and we use a ton of data science and therefore data to do the kinds of things that we do. And so data and as applied to microservices is a core thing that we do. Before that, I was sort of a roving CTO as a service, my friends used to say. I used to help a lot of companies try to figure out whether they need to move to microservices, and if so, how they can do it in an effective way. And earlier, I was director of engineering at Google for Google App Engine. That's Google's platform as a service, like Heroku or Engine Yard or Cloud Foundry. And then I spent about 6.5 years at eBay as the chief engineer, working mostly on the search engine, which was, a third of our infrastructure and is used in a bunch of areas, the obvious areas of searching for things on the site, but lots of non-obvious areas as well. So I learned a ton about how to build big systems, all the mistakes, that you could imagine making, I and my teams have made. And so you're going to get a bit the benefit of what we have learned from that. Cool. First, a little bit about Stitch Fix, again, just because it'll motivate the data and the data science. So we are sort of the opposite, I suppose, of a normal clothing retailer. So rather than coming and shopping on our site, what if you had an expert to do it for you? So you actually fill out a really detailed style profile about yourself. It might take you 15 or 20 minutes. We'll ask you a bunch of questions about your height, your weight, your size, your age, your parental status, your occupation. Do you like to flaunt your arms? Do you like to hide your hips? All these kind of pretty personal questions. Why do we ask you those things? If there's a person in your life, and maybe it's you, but if there's a person in your life that knows how to choose clothes for you, what does that person know about you, right? What does that sibling, that best friend, that spouse know about you, whether that person is, aware of it consciously or not? And those are the kinds of things that we ask. So you fill that out. We're going to send you 5 hand-picked items in the mail in a box. Hopefully you will enjoy them. You keep the ones that you want and you'll pay us for those, and then you return the other ones for free. Behind that, like I said, is a ton of data science. So in the group that I work on, I joined 2 years ago. We were 25 engineers then. We are now 125. And we have about 80 data scientists and algorithm developers in addition to those 125 engineers. And that ratio of sort of near one-to-one between engineering and data science, we believe is an entirely unique ratio in our industry. There are maybe a few financial companies that have that ratio, but not at this scale, if that makes sense. Like a hedge fund does not typically have 100 engineers and 100 data scientists, even though they would have maybe an equal ratio. What do we do with all those data scientists? It turns out everything. So every aspect of the supply chain of a clothing retailer, we apply data science to. So trying to figure out what clothes to buy, in what quantities, in what size breakdowns, and what locations around the world, around the US should we store them. Inventory management, so there's a very interesting traveling salesman-like problem of when somebody's picking those 5 items to go in your box. Like that's exactly a traveling salesman problem, which as the computer scientists in the audience know, that's NP complete and challenging and all. We think about logistics optimization, so what's the cheapest way to ship a thing to you through the actual physical world fastest and get it to you on time. The styling recommendations, which I'm going to talk about a bit in a moment, and then more prosaic things like demand prediction. We are a physical business, as many I'm sure of you are, and so if we guess wrong about the demand that we have for our service, like that's a disaster. So when I used to work for eBay or for Google in more virtual businesses, if we had 2x the amount of traffic to the site as we were expecting, like we pop champagne corks, if that happens at Stitch Fix, like it's a disaster because it means half of our customers we can't serve well. Does that make sense? Cool. And so in all these things, as you'll see, they are aspects of humans and machines working together. So I'm going to mostly talk about the machines part. So the styling function, this is what we call the choosing the things that go in the box to you. So from your experience as a customer, like you can imagine we have all this inventory floating around in our warehouses, and then magic happens, and then a box shows up, and you love everything. There's actually a little bit more to it than that. So there's a first phase, which is every day we take every piece of inventory times every client, and we compute a predicted probability of purchase. What is the conditional likelihood that if we send Randy this sweater, he will keep it, right? So let's imagine, I don't know, 64% chance that Randy will keep this cashmere sweater, 47% chance for the jeans, although they're stretchy and very comfortable. By the way, stretchy jeans, guys, that's a revelation. I didn't know about it. It's awesome. Women were like, women, you knew this forever. Like, we just don't even know. Anyway, and then, you can imagine, like, I don't know, 72% chance for the hiking boots, because that's all I wear. Yeah, so that's a ton of machine learning, and that goes into these personalized scores. And to be clear, that's personalized for that piece of inventory for you. Does it make sense? Like those scores are different, for Michelle, for Chris, for me, et cetera. Okay. So those go through the stylist, and who is the human curator of those recommendations. So it's not like the machines directly decide what to send to you. They decide what to recommend on your behalf to the stylist, and then the stylist puts together an outfit or responds to a particular request that you have. Like you might say, I'm going to an evening wedding in Manhattan, send me something appropriate. And at the moment, our machines don't know what to do with that request, but the human totally does. They're like slinky black dress, like the humans know that. Cool. So ultimately, that ends up in a box that you hopefully enjoy. Great. As Mike mentioned, I've worked at a couple of these companies, as I said as well, eBay, Google, and what I'm going to talk about at the moment is how those companies have thought about maybe when they were starting as smaller businesses where we didn't know whether they're going to be successful or not, and how they have evolved over time. So eBay, depending on how you count, is currently on its 5th complete rewrite of its infrastructure. So famously in 1995, Pierre Omidyar, who was the founder, spent the 3-day Labor Day weekend learning about this new cool thing called the web. And he wasn't planning on quitting his job at Adobe and founding a business and becoming a billionaire, although that's what happened. But he was playing around with this idea of auctions, and so he created this thing that ultimately became eBay. So that was monolithic Perl. It was very much not scalable, nor was it intended to be. The next iteration, which we called V2, was a monolithic C++ application, which at its worst was 3.4 million lines of code in a single DLL. We were hitting compiler limits on the number of methods per class, which is what? 16K. I bet I'm the only one in the audience that actually knows that. Because that's a limit we actually hit. Yeah, crazy. So if you guys think you have monoliths, I'm sure you do, but that's a monolith. Like, all right. The next iteration was a rewrite in Java. I think you can't really call it microservices, but you could call it mini applications, right? So a particular page or set of related pages on the site would be represented by a Java application, you know, the selling application, the buying, search, some part of customer service, et cetera, and there actually ended up being 220 of those different applications, each represented by a pool of machines, et cetera. And then now it's fair to characterize eBay as a polyglot set of microservices. Twitter has gone through a similar evolution, so depending on how you count, it's probably on its third generation. Twitter famously was the world's, and maybe still is to be honest, the world's largest Ruby on Rails application. It was a monolith. The code name was the monorail. Yeah? Those guys are clever. The second iteration was pulling a bunch of the front-end stuff out into Java, a bunch of the back-end out into services, mostly written in Scala because Twitter was a very early adopter of Scala, and now it's fair to characterize Twitter as a polyglot set of microservices. Amazon has gone through a similar evolution. So it started as a monolithic Perl and C++ hybrid, which you can actually still see evidence of in some product details URLs on the site. So if you ever see Obidos, OBIDOS in an Amazon URL, that is the code name of the original monolithic application. And those still exist in a bunch of, not because the application still exists, but because search engine optimization and PageRank, and they've accumulated so much, you know, value behind that particular URL that they basically can't change it. Cool. The next iteration was a breakup into service-oriented architecture. Now we would probably call it microservices. They would not. But breakup into services, mostly written in Java and Scala at the time. That took the 5 years from 2000 to 2005. So anybody who's a retailer, like you're a competitor of Amazon, right? As we are, because like if you're in retail, Amazon competes with you. Also, if you're in infrastructure, Amazon competes with you. That's another thing. But the wonderful genius of Jeff Bezos, among so many genius things that he has done and has thought, people maybe don't remember now, but like in 2000 to 2005, Amazon was not doing that great as a business. Like from a profitability and revenue perspective, they were basically flat for most of those years. And so you can imagine there was a ton of pressure from the board and from Wall Street for Bezos to like, why don't you guys, I don't know, go into some more businesses beyond book selling? And he said, no, we're going to break up our monolithic architecture and we're going to come out at the end of it much stronger. And look what happened, right? AWS, Amazon does legit compete with every retailer on the planet, and they're doing a great job at it. So, you know, if you take nothing else away from this talk, like, if you do this stuff right, you can become Amazon, yeah? Yeah, well, yeah. If Amazon doesn't get there first, but yeah. Cool, okay, and then it's fair to characterize now Amazon as a polyglot set of microservices. Cool. Does there seem like a pattern here? Yeah, right? There's two parts to this pattern. None of these successful companies actually started with microservices. Every single one of them was a monolith out the gate, and that was totally correct. But past a certain scale, past a certain scale, not every solution, not every problem, but past a certain scale, everybody is going to co-evolve to something that looks a lot like microservices. Does it make sense? So maybe it's only 0.1% or 0.01% of companies that have crossed that threshold, but everybody who has crossed that threshold at some point has co-evolved in this convergent evolution to something that we would now call microservices. So Martin Fowler, who is wonderful, wrote the refactoring book, is justifiably famous for many reasons, likes to say this: the first law of distributed object design is don't distribute your objects. So if you can live in a monolithic world and it meets all the criteria of things that you do, don't do microservices because that's what the cool kids are doing. Do exactly what is meant and will help your business, and then do that and be successful. Here's what I like to say. If you don't, though, end up regretting your early technology decisions, you probably over-engineered. It's possible that there was an eBay or an Amazon competitor in 1995 that started out building a distributed system. There's a reason why we've never heard of that company, right? If you've started out of the gate and they're like, well, in 2 years or 5 years or 10 years, we're absolutely going to want to have a distributed system, so we better get started now, that's a great way to not have a business, right? When you're a startup, or even when you are a starting up new project within a larger company, your goal is to figure out whether there's an actual market for the thing that you're building, build it and meet the needs of your early customers, and only if you should be so lucky as your customers are broader than you can support with your old architecture, only then should you consider re-architecting. Does this make sense? Cool. So I kind of want to give this apologia beforehand, and then I'm going to spend the rest of the time telling you how to do microservices, but I do want you to say, like, just because I think personally microservices are a great solution for the kinds of companies that I've worked at, it doesn't mean that they're the right solution for everyone. Cool. All right. Microservices. We actually haven't even defined them today. They are single purpose. They have a simple, well-defined interface, and they are modular and independent. And I love how Chris formulated this idea. Micro is not about the number of lines of code. It is not about how long it takes to write or whether it fits on a page or not. Like, none of that stuff matters. Micro means the scope of the interface. Does it make sense? The scope of the interface. It does a single thing. It does it very well. Cool. One thing, okay. Anybody who has been around software as long as, look at my head, I have been, or longer, is going to say, well, all these things just look like components, right? This is just good software engineering, right? Who feels that this is just good software engineering? Yeah, okay. Microservices are nothing more than service-oriented architecture done properly. Okay? That's what I believe. But what is the thing that I will say I was part of this? What is the thing that we missed, or for a large portion of we, the first time around in service-oriented architecture? It's that we did not think about the persistence. We did not think about the database. Does it make sense? The first iteration at eBay in 2008, while I was there, eBay made a good attempt, good college try at moving to a service-oriented architecture. They built and designed some excellent, well-defined services above a sea of shared databases that the applications were already using. So the services were very well designed. Some of the best minds at eBay were spent on designing them and building them. So they were great. There was nothing wrong with the services. But the fact that they were using this whole sea of shared databases didn't own their own persistence. And also, those shared databases were also available to every other application, meant that there was no incentive for the application owners to move from what they were currently doing and was currently working over onto the services. Does it make sense? So they forgot about the most critical thing, which I'm going to spend the rest of this talk talking about, which is how to manage data within a microservices environment. Does it make sense? Okay. What do we mean, Randy, what do you mean by isolated persistence? That's a great question. I'm glad you asked. I will tell you. There are two ways I think of to think about isolating the persistence for a service. The first way to do it, and it's pretty obvious, is the same team that builds the service is also kind of building or operating and maintaining a database, right? So we might have our own instance of choose your favorite database, Oracle, MySQL, Postgres, SQL Server, whatever. We store to our own particular instance of that thing, and it's just ours within the service. This is a totally legitimate strategy, and we absolutely use this strategy at Stitch Fix. Another equally equivalent approach is use some kind of persistent service, whether that service is provided maybe by another team at your company or a third-party provider like a cloud vendor or something like that. So store to your own schema, right, within some shared persistence thing. So this could be implemented as, store to some particular instance of Dynamo, some instance of the relational database service at Amazon, or a cloud data store if you want to use Google, as I used to work for, Spanner, which is another Google thing, or as is a legit thing to do, although there are definitely trade-offs. Imagine you have some monster Oracle database and it's sliced up into individual smaller schemas, and each of you takes a slice of that. That's another legit way to approach this problem. But the key thing is the isolation. Does it make sense? The key thing is that the only way to get data in and out of the data that your service is going to use is through your published service interface. Does it make sense? That's what we mean by isolated in this context. Cool. Okay. All right, so microservices, as with all architectural styles, as Chris introed us to, have some pros and have some cons. I want to briefly talk about the pros, I want to acknowledge the cons, and then I want to talk about, again, in detail, how to do data in microservices. So the pros are, one of the pros is that each individual unit in this architecture is simple, right, by comparison to a big monolith. We can now independently scale and independently tune the performance of those things, as Michelle pointed out. We can independently test them and independently deploy them. So that has nice properties for feature velocity, agility, et cetera. And we can also choose the optimal technology stack. So we might not all have to be in Java. It might be the correct thing to do a particular microservice in, I don't know, Haskell or something like that. And then also, as was pointed out in one of the breakouts, it's also a security boundary, right? It's also a place where, as distinct from a monolith, the microservice, you can have much tighter security bounds around what that service can and can't do with sensitive data, with sensitive networks, et cetera. There are, of course, cons to these things as well. So while each unit is simple, there are now many cooperating units, and there's some complexity associated with the relationships. We are exchanging in-process latency for network latency, right? So we're changing, wow, everything is super fast, and I can be very chatty with a class, you know, an instance of a class in process with me, but I have to think a little more carefully about that when I talk over the network. I do have to deploy, as Michelle pointed out, much more sophisticated approaches to deployment tooling and monitoring. And also, there's an overall increase in the complexity at the system level as distinct from like within the monolith level. Does this stuff make sense? Cool. Okay. Why in the world would we re-architect? I can think of 3 reasons. The first reason is for velocity, right? It might be that the monolith is constraining my teams in terms of the ability to like work together and move forward. This is by far the most common reason that people say, oh, we can no longer live in this monolith because my team is slowed down. Similarly, there's a scaling or a load or a, you know, performance bottleneck argument where vertical scaling of the monolith, like we kind of run out of gas in terms of vertical scaling. It becomes a single performance bottleneck, a single failure domain. And then one which is rarely anybody's first reason, but often everybody's secondary reason, is this idea of independent deployments where I can make iterative modifications to one service without having to deploy the whole system. Does this make sense? So let's imagine we're going to do one of these migrations. We're going to take our monolith from our successful business, and we're going to migrate to microservices. I will again use a wonderful quote from Martin Fowler. So please don't do it as a big bang, let's go dark for 2 years, but then it'll turn into 20. Let's go dark for a couple years and then emerge later. So Martin has this wonderful, you know, sarcastic quip, which is the only thing a big bang migration guarantees is a big bang. So don't do it that way. Instead, let's do it incrementally. And so I'll talk a little bit about how we were approaching that at Stitch Fix. So our version of the monolith problem is that we have a monolithic shared database. We never built a monolithic application, but we do absolutely have all the interesting entities of Stitch Fix in a shared database. So this diagram, the boxes and lines here don't represent, they're actually like 70 of those boxes, but the lines wouldn't look good. Anyway, so that is our problem, is that we have this monolithic shared database that everything uses for the interesting entities. And our solution is that we want to decouple applications and services. So how are we going to do it? So step 1, so I reduced the number of boxes and lines just so that it's a little bit more tractable. But imagine that there are still 70 applications and 200 tables. Okay. So let's imagine there are two applications, though, and 3 tables. So first off, we're going to create a service that is going to be, you know, single purpose, have a nicely scoped interface. We are going to, the next thing that you do is you point the apps at the service as distinct from the database. Now, that flip that I just did, moving those lines, like that is the biggest amount of work. Right? That is the hardest step. So just because I moved some lines on an architecture diagram, don't think that I'm thinking this is the easy part. This is the hard part. But once you have done this, and all the applications that were otherwise, in this example, using the client table are instead using the client service, now we can move the client service out of that shared database into a database that is owned solely by that service. Does this make sense? All right, cool. Well, now that was probably several engineer years of work that I just talked about. Okay, fine. But that's how you do it. And then the next thing is we do the same thing for the item service. Like we create an item service and we point all the things that used to be using the table to the service, and then we move the table out of the shared database, and we do the same thing for styles, which is at Stitch Fix our concept of the metadata around our inventory. So you just keep doing this over and over again, and hopefully, you know, you will be done at some point. Does this kind of make sense? One other minor point that I want to make is when you're in one of these interim phases, when you're in this phase where the data is still in the monolithic shared database, but at the same time you have this service that the applications are using, this is actually worse than the starting point. I see knowing nods. Why do you mean this, Randy? Why do you say this, Randy? It's because now, in this moment, you have all the problems of the monolithic database and you have all the problems of a distributed system. So you are not done until you are until that data is all the way out of the monolithic database or out of the monolithic application into the service. Is it making sense what I'm saying? Yeah, you have to go through some, like no pain, no gain. You have to go through some pain in order to get stronger and, get out of there. Cool, okay. Rinse and repeat, excellent. Okay, oh, and then these are actually the boundaries. Yeah, the boundaries that we draw for the services are not just around the business logic part, but also around the data part, right? Does this make sense? Cool, all right. So, everything is wonderful, we've solved all of our problems, all done. Well, no. There are a lot of wonderful things about a monolithic database. Like you can do sharing data very easily. You can do joins very easily. You can do transactions very easily. I still want all of these things. So the rest of the talk is going to be about how can I get as much of these three things as I would like in a microservices world. Does that make sense? All right. But first I want to give you another tool in your architectural toolbox. I want to talk about events. So I believe that we as an industry underutilize the power of events. So an event as defined by Wikipedia is a significant change in state. I like to think about it as a statement that something interesting occurred. So most of us have cut our teeth on building, traditional three-tier applications. So there's presentation, there's business logic, there's persistence. But I think we are missing something. I think if we only think about those three tiers, we are missing a first-order concept of a state change, which I'm going to call an event. And we'll talk a little bit about this as we go forward, but typically, we'll produce, one of the services or one of the parts of our system will produce an event when some interesting thing has happened, when something has changed, and then there will be maybe nobody, or maybe one person, or maybe several entities around our system that are listening to that event and doing something interesting. Okay, I want to connect up microservices and events, and Chris in his intro has a wonderful diagram, which is much better than what I'm going to have on this slide, but that's cool. They're all very compatible. So I think that events are a first-class part of a services interface. So a service interface obviously includes the synchronous request-response part, right? It obviously includes whatever it is, REST and JSON or gRPC or SOAP or, God help you, Corba, like all these things. Corba? No laughs of Corba? All right. This is a crowd that should remember that. I have all the scars from Corba myself. Anyway, so whatever you use for your synchronous request response thing, that's obviously part of your interface. But also part of your interface is all the events you produce, all the events you consume, and also if there's any background ETL, like extracting stuff for analytic systems or maybe a bulk data load, all that stuff is also part of your interface. Does this make sense? And when I say part of your interface, I mean it needs to be maintained in a serious, principled way. It needs to be backward compatible. You need to think about it very carefully as a first-order concept. Is this making sense? So the way I would just say it in general is an interface to your service is any mechanism that gets data into it or out of it. Okay. So now that we have events in our toolbox, now we can start to attack first shared data, then joins, then transactions. So shared data, I will set the problem statement. So in a monolithic database, it is very easy to leverage shared data, right? I just simply point at the, metadata table or something, and I use it, and it's all good. Great. But where is this shared data going in a microservices world? I will give you three options. But first, I will give you one other little architectural principle. So this, as I'm sure many of us have come to believe and learn, if there is a piece of data that is interesting for your business, there should be one system and one system only that is the system of record for that piece of data. Does it make sense? Every piece of data, a customer address, a box that we would send at Stitch Fix, there is one and only one place in our system that is the canonical system of record for that data. Every other place that we remember the customer address or what's in the box or whatever is and every one of these words is important, is a read-only, non-authoritative cache. I'll let that sink in for a moment. Every other place where we know about the customer address should be read-only, yeah? Should be non-authoritative, like you can ask it what the customer address is, and it might even tell you, but it's going to be stale, yeah? And it's a cache, which has that similar idea of it is not the system of record. Read-only, non-authoritative cache. All right, so there is going to be a system of record for customer, there is going to be a system of record for all these things, and there are many other places in our system. In this example, styling needs to know about the customer, searching for customers needs to know about customer, the billing service needs to know about customer, but they are not the system of record for customer, yeah? The customer service is. Does it make sense? Cool, all right. Great, so 3 approaches to shared data. The first one is just look it up. This is totally legit. So in this particular example, imagine we have a fulfillment service at Stitch Fix which is going to send a customer a box. That fulfillment service needs to know the customer's address. So when the fulfillment service needs to know what the customer's address is, it could just ask the customer service, hey, what's the customer's address? And it could be told. This is a totally legitimate way to do it. We do this all the time at Stitch Fix. Sometimes this way of approaching it doesn't meet like reliability requirements. Maybe we want the fulfillment service to be able to continue to ship boxes even if the customer service is down. Maybe the customer service can't handle the load of the fulfillment service asking it for addresses all the time. Like there are legitimate reasons why this might not be the appropriate solution. So we'll try number 2, which is an asynchronous event combined with a local cache. So here's what I mean. There is a customer service which owns the customer data, so that's still the system of record. The customer service, when the customer updates her address, it will send an address updated event out into the ether. One of many services or interested consumers might be the fulfillment service, which would listen to that address updated event and remember locally, cache locally in that read-only non-authoritative way, cache the customer address. Does this make sense? Cool. Again, a totally legit, approach 1 is legit, approach 2 is legit. These are totally legitimate ways of doing it. The reason why you would choose one over the other is basically the ilities, right? Is what kind of response do you want to load? What kind of response do you want to failures? Okay. There is an approach 3 for shared data that is more like shared metadata, so slow changing things. So at Stitch Fix, we have a lot of it. So things like, in retail, we talk about size schemas. So this is like small, medium, large, extra large, or for women's numeric sizes like 2, 4, 6, 8. That's a size schema. It is rare to have like a new extra, 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 extra large. Like that's rare. It's not that it doesn't happen. It actually does happen, but it's rare. Colors. So again, very slow changing, right? We do have to have a canonical standardized representation of color, and again, that's something that's metadata. Fabrics, the U.S. states. So I hope, I am a big fan of service-oriented architecture, believe me, but I hope nobody has produced a service which what are the U.S. states? Oh, here are the 50, Randy. I hope you never, that's like too far. That's a bridge too far for me. If and when, and I hope this is actually true, I hope someday Puerto Rico will actually become a state. I certainly hope our government will send them some help also. That's another thing. Anyway, that maybe there will someday be a 51st or 52nd or whatever state. That's legit, but we're going to have plenty of time before, we don't have to update the service in the moment for that. Does it make sense? That's not that will be known, months and years ahead of time. Cool. Does this make sense? Great. Oh, and what's the solution here? It's simply distributed as a code library, right? Think of it as shared code. So that's actually what we do, is for things like size schemas and colors and fabrics, we version them by versioning a particular library or a particular a code distribution mechanism. We use Ruby, so that's why I use this Ruby thing, but that could be a jar, or that could be, the module in your favorite system. Does this make sense? Okay. That's shared data. Now let's talk about joins. Here's the problem statement. A monolithic database makes it really easy to join tables together. All I have to do is add a few additional characters to my SQL statement, right? So instead of it's select from A, now it is select from A, inner join B on some join condition, all done, super simple, thank you, we're great. But once we have split this data across microservices, this is pretty hard. So how are we going to deal with it? There are two approaches here, and they're pretty obvious, once you think about them, and I will explain them in detail. So the first approach is just simply join in whatever application needs the things together, right? So in this example, I want to build an order history page. So I want to show for a customer all the boxes that we've sent to her. And so one could imagine certainly that we would build this page by first going to the customer service and getting some information about her, and then going to the orders service with the customer ID and saying, return me all the orders for this customer. Does this make sense? I mean, everybody's nodding, but this is every web page on the planet. Yeah, this is every web page except for the ones where all the data comes from a single service and a single call. Yeah? If you can serve your whole thing from a single call, yeah, you don't need this. But if you ever make 2 calls, this is it. Okay, so you guys do this all the time, as I'm sure you appreciate. And this is a totally legit strategy. There's nothing wrong with this. But again, why would you not choose this? Maybe, again, there's an ility argument. Maybe I want to be able to produce this page without the order service being up. Maybe it's too slow to build the page out of, querying things from piece parts, et cetera. Okay, so approach 2 is, in a microservices world, is let's have a service that materializes the view. And I'm very intentionally using database terminology here, but I'll try to use lots of different words for the same concept. But the idea is, and I'll use a different example here. So let's imagine that we want to have a service that at Stitch Fix remembers all the feedback that we've gotten from customers about particular items that we've sent, right? So we've sent this, cashmere sweater out many hundreds of times to our customers, and every time we send a box to customers, we've sent 5 items. So let's imagine that we have this item service that produces events that say, okay, now there's a new cashmere sweater in our inventory. A new kind of inventory, right? There's a new style of cashmere sweater which is represented, one instance of which is the one I'm wearing. And then there's also, you can imagine, an order feedback service, which every time we send an order to somebody or a box to somebody, when that client tells us whether he or she liked it, that we would remember the feedback. Does that make sense? Okay. So both of those would produce events. So the order feedback service would produce an event every time we got some feedback about a box. Maybe it would produce 5 events, 1 for each item, something like that. But in any event, there's an item feedback service which is listening to both of those classes of events and maintaining that join inside that service. Does that make sense? This is why I call it materializing the view, because if that's familiar to you from using an enterprise class, i.e. you pay for it, relational database like SQL Server or Oracle or something like that, you have this tool in your database toolbox already. If this looks unfamiliar, if this technique of joining in some other service seems unfamiliar, then I'm going to give you some examples where you use it all the time. So as I mentioned, all the enterprise class database vendors have an idea like this. Almost every NoSQL system that you might want to use, so Cassandra or React or Voldemort, all these NoSQL systems, you typically are representing in a cached way the query, rather than in relational databases where you're writing the individual things on the write time and then you're putting them all together at the read time. Most NoSQL systems are the reverse, where when you're trying to write something, you actually write it in parallel to a couple of sort of stored queries and then read them fast. Anyway, so if you use NoSQL systems, you're probably doing this without knowing. Almost every search engine, if you have a search engine at your company, it's almost always a join of a bunch of different entities' information, and then every analytic system on the planet works like this. Does this make sense? Is this feeling a little bit more familiar? Cool. All right. That is joins. The last thing I want to talk about is transactions. So so I was able to solve both the shared data and the join problem pretty straightforwardly in microservices. This is the one where I'm not going to be able to give you everything you want, but I'm going to be able to give you something that's maybe okay. All right, so in a relational database, one of the things that relational databases are excellent at is doing transactions. Okay, so it's really easy to do transactions across multiple entities. So in this example, we're just going to say begin, and we're going to insert some things into A, we're going to update some things in B, we're going to commit or roll back the transaction, it's going to be ACID, it's going to happen all together or not at all, we're going to be very happy, we're going to be immediately consistent. But once we have split this data across a service for A and service for B, we basically no longer have this transactional tool in our toolbox. So instead, we're going to talk about something that we call a Saga. And Chris, gave me a little nod, ahead of time about this in his talk. But I guess I want to take a step back and answer the question, why can't we do a distributed transaction here? Nobody at scale really does this in practice. So conceptually, academically, it is absolutely possible to do a distributed transaction. Like, there are plenty of coordination protocols, 2-phase commit, 3-phase commit. There are lots of communication protocols with lots of smart people have spent many decades researching. The problem is that because they are coordination, they are almost by definition, they are a performance killer, a scalability killer, and a reliability killer, right? This is not because smart people didn't do good work. It is part of the physics of the universe. Does it make sense? Like, if I'm trying to coordinate a distributed transaction across A and B and C, by definition, A and B and C all need to be up and responsive quickly in that moment. Yeah? So if any of them is not available, or if any of them is slow, that transaction across A and B and C is going to fail. And so again, this is just a fact of the universe. This is not a fault of any of the wonderfully well-meaning academic researchers that have done this work. And even the people that have implemented it in industry. So there's a guy, Pat Helland, who is very well known in the distributed systems community. He spent many years working on SQL Server at Microsoft. He went to Amazon for a while, back to Microsoft. Now he's the chief scientist or something at Salesforce. Brilliant guy, so funny, so hilarious. And he likes to say that 2-phase commit is the anti-availability protocol. And he should know because he built it. He built it. Okay, great. So what are we going to do instead? It's not like there's no hope. Here's the hope. Think about our process. Think about the thing we want to do, the transactional unit of work that we'd like to make out of the A thing, the B thing, and the C thing. But think about it as a workflow, or more formally, think about it as a state machine of individually atomic events or transactions. Okay, what do I mean? We're going to re-implement this A, B, and C transaction as a workflow of first I do A transactionally with the A service. Okay? A is going to produce an event. B will listen to that event. Then B is going to do its thing transactionally within the service, okay? B is going to produce one or maybe several events. C is going to listen to that. C is going to do its thing transactionally within its service. Does it conceptually make sense? A is going to do its thing, event happens. B is going to do its thing, event or multiple events happen. C is going to do its thing. Now you say to me, the clever among you is like, yeah, but how do I do a rollback? Great. Okay, you roll back by applying the compensating operations, the undo operations in the backward order, right? So let's imagine we got all the way to C. We need to undo this thing. C does its undo, produces one or several events. B does its undo, produces one or several events, and it goes back to A. Does it at least conceptually make sense? Okay. Your next objection, one of your next objections will be, yes, Randy, but before, when I had an ACID transaction, it was atomic and consistent and isolated and durable, and nobody could observe those intermediate states, right? I got A and B and C, and it all happened, or it didn't happen at all. You're right. You got to give that up. So this is neither, sorry, it's physics. So this is not atomic, this is not consistent, this is not isolated. It is durable. It is durable. So you at least got the D. No, so the correctness behind your objection is that you can observe intermediate states. Does it make sense? The intermediate states are observable. So what are we going to do about that? We're just going to live with it. But we're going to live with it happily. Why? Because many, many common systems that you use every single day of your lives do exactly this. So whenever I would like to, let's imagine Michelle wants to pay me some money through credit card. I wish that would immediately go out of her account and immediately go into mine. Anybody think that happens? No, it super does not. It goes out of her account. She doesn't have access to it. The bank keeps it for like 3 days, which is why the banks have all the money. Oh, and that helps Michelle in her job. Awesome. I didn't even realize that. Cool. This is great. That's why, I get it, all right. So stays in the bank for 3 days, which is why they have all the money, and then finally it ends up in my account. Does it make sense? That is a workflow. And we can observe that intermediate state, right? We can say, what is the state of this money? Oh, well, it's a pending transaction, like it's out of Michelle's account but not yet in Randy's. Does it make sense? Similarly, expense approval. So Molly here, who's been totally awesome and a wonderful organizational genius, has put all this. Yeah, all right. She's not even listening. We love you, Molly. All right, we'll tell her later. I'll thank her personally later. So she has been wonderful about, hey, speakers, if you incur any expenses, give us all the information. And so they'll process it. Well, what do you think is going to happen? Do you think that as soon as I, hand her my receipts for, the lift that I took here or whatever, that immediately I'm going to get my money? No. She's going to submit it, and there's going to be an approval process. So, Mike will have to approve it, and then Mike's boss will have to approve it, et cetera, all the way up to the chancellor of the University of Minnesota, possibly. I don't know. But you see what I mean. And then it will cascade down, approved or not approved, and then I will get my money. And that's legit, right? That approval process is exactly a workflow. And the idea of a pending or transitional state is like a first order concept here. Does it make sense what I'm suggesting? Cool. Travel. So, if these analogies weren't good enough, one that occurred to me while I was sitting here is I flew yesterday from Chicago to Minneapolis. I left Chicago, and an hour and a half later, I arrived in Minneapolis. That was an intermediate state, right? So I was in Chicago, and that was, a sort of stable place. I was there for a couple of days. Then I, go through this transitional state, which is observable, like where is Randy? I don't know, somewhere in the air among the upper Midwest. And then land in Minneapolis, and now I'm in another terminal state. Does it make sense? So, yeah. So basically any multi-step workflow, if you can think about your problem, or rather, please try to think about this problem as a multi-step workflow, and it will be a lot easier for you to reason about it. Does it make sense? The other thing I want to say about this is, if you're a database person, most of the databases that you operate today, you actually can observe intermediate states. So who is familiar with isolation levels in your database? Who runs at serialized? No hands. You can observe intermediate states. The people who know what I'm talking about know what I'm talking about. So serialized means that there is formally a serializable or linearizable view of the things that happen in your database, which is essentially ACID. It is the strong ACID property. Most people run at read committed or even read uncommitted. In both those cases, you can observe intermediate states that so read committed means like you can read things, before everything's all done. You read the committed stuff, but the rollbacks like can screw you up. Anyway, the read uncommitted means like you can read dirty stuff. Anyway, I just submit to you that even if you think you are running an ACID compliant database, you probably aren't. Why? Because if you ran with serialized, it's what? A performance killer. Yeah, okay, cool, great. Okay, so a thing that we might notice about this is that A and B and C are doing very simple event-driven processing. Does it make sense what I'm saying? In response to this thing that I start with A, and it goes to B and goes to C, there's very lightweight logic here. It's stateless, and it's also triggered by an event. So, since we are in 2018, I must point out that this is potentially a very good use for functions as a functions as a service, or thing that we incorrectly call serverless. Does it make sense what I'm suggesting? It's not the only way to solve this problem, but a legitimate solution in 2018 to problems like this, where I have this chain of processing that starts in one place and it's triggered by an event and it's stateless and it's lightweight. A very nice and easy way to deal with this is functions as a service. So that's Amazon Lambda, that's Google Cloud Functions, that's Azure Functions, that is Iron. Like there's a couple of things. Whisk, I guess, is if you have run your own data center. Anyway, there are ways to do some functions as a service whether you're in the public cloud or not. But does this conceptually make sense? I'm not saying this is the only way to do it, but if anybody asks you or you ask yourself, like, what's serverless good for? This. It's great for this. It's good for other things too. And then I guess the other point that I want to make is this is a state machine, right? So all the stuff that we know about formally verifying the correctness of as I am transitioning through interim states in this graph in my state machine, do I reach a terminal state? What are the terminal states in this state machine? All those things that some of us might remember if we studied serious computer science, those are now valuable again, right? Those pieces of your computer science education that you maybe haven't had to pull out for a while, all the things that we know about state machines and automata theory, all these kinds of stuff, like these are actually relevant. Why? Because they give us formal ways of thinking about processes like this, where we want this workflow to terminate either in a payment from Michelle to Randy or no payment at all. Does it make sense? Cool. Okay, so together we have explored how to do shared data in microservices, how to do joins in microservices, and how to do transactions. And you will notice that in all three of these cases we leveraged events. So I leave you with events are that tool in your toolbox that you should pull out probably more often than you are today. Thank you very much.
Here we have, again, the standard speaker package, which will keep you warm, keep you liquidity, and keep you writing. But let's
just my
see.
sweater.
It does. You should, you could sell that on Stitch Fit. So anyway, questions for Randy?
I can repeat the question too if you want to get started.
In all of these cases where there's eventual consistency, if something breaks down, how do people implement reconciliation processes or go back and clean up the cache and make sure it's correct?
Yeah, so how do you do reconciliation or cleanup in that rollback case? Yeah, so I'll go back and show the diagram again. Yeah, how do you do that compensating operation? There are several ways to do it. I guess it's like the margin is too small to, no, go ahead.
So what I'm saying is, what if that fails? The rollback
What if the rollback fails? Yeah. Yeah.
Go clean up the whole thing.
Yeah, sure. So I will give you an answer. The broader answer is there's a wonderful talk by Katie McCaffrey, who now works for Microsoft, on sagas. Her whole talk is about sagas, and she talks in great detail about the requirements that you have to have around the compensating operations. So I will try to reproduce them, and I will probably forget one, but they need to be idempotent, and you need to keep trying until they succeed. Does that make sense? Also, and you hinted at it, it is also a legit strategy to have another, you said reconciliation, and that word very specifically. You can use another like a batchy reconciliation thing to periodically check, am I in one of these interim states? But does it make sense? But again, I want to go back to, I know you got it, but I want to go back to what I was talking about, the state machines and formally thinking through whether you are going to correctly transition to a terminal state or not. If I can restate your question, that's exactly your question. Does it make sense what I'm saying? I see you nodding, but that's cool. Nodding and smiling, so good. Yeah, you exactly asked the question, hey Randy, what if I don't terminate in a terminal state? And yeah, you got to make sure that you do. Cool, good question.
So my question is actually about the events, which you hit at the very end, and how much data goes along with the events. So there's, you have this asynchronous architectures, and you can send just a notification that then they have to query, or you can send the data with the event, or there are a bunch of ways to do it. How would you look at that?
Gorgeous, yeah. Chris is not paying attention, but he should be laughing because this is every time I give this talk, first well, in some order, it's either the event ordering and idempotence question, which is that one, or the how do you deal with failures question. Awesome. So like clearly the second hour of this talk should be that. And as I joked in San Francisco a couple of months ago when Chris and I spoke together at another conference, I joked that I keep meaning to give an event masterclass, and Chris's wonderful response was, and you should give it at least once. All right. Okay, how do you deal, what type of data should be carried along with an event? Again, I will give you a reference and then I will answer the question. So the wonderful reference, which is quite quick, 18 minutes, is Martin Fowler's keynote at Go to Chicago 2017. It was called the Different Views of Event-Driven Architecture or something like that. It's a fantastic, both beginner and intermediate and advanced, it's like accessible to everybody in the room, evaluation of the different ways that you deal with that. Okay, so if you carry the data along with the event, that seems cool because now the receiver of the event doesn't need to go and get the data itself. The problem is if you need the events to come in a certain order, the receiver of the event might have received them out of order. Does it make sense? And so if you carry the current state as of when the state that's in the event can only be the state as of when the event was produced, but the state might be different depending on the event ordering and like when the event is received. I don't think I explained that very well. So a lot of times, and this is what we did at eBay, we do not carry the data along with the event. Instead, we use the event, as Mike said, as a notification, and then we read back to the service to find the current state of the data. I see lots of nods. This is the way that we deal with event ordering. Does it make sense what I'm saying? If I need to process the events in some particular order, A, then B, then C, then D, and I get them out of order, a way to deal with that is to always read back to the source service and find out the current state, because that will deal with that problem. There are many other slightly more advanced techniques, which we can all talk about, that culminate in things called event sourcing, which is about how to represent the states, no matter how you have transferred the state from the producer of the event to the consumer of the event. We might remember our state as a series of events, and that can be another way of dealing with ordering. Like maybe so you can defer the ordering or the reordering of the event until it's actually being asked for. I don't think I did it. It's like, that's why this has to be the master class, because like, the answer to this is its own talk. Actually, it's probably a PhD thesis that somebody else has written, but yeah. Cool, good one.
You guys need more coffee. What is the problem? All right, but let's think, oh wait, we have one more.
Wait.
I just have to.
I'm hoping it's the idempotence question.
Yeah. If it's the idempotence question, it better not be asked by one of my software architectures.
Sorry to disappoint, it's not that question. So when you're splitting out the service, so you have the monolithic database and you have the particular like client service in front of it.
Yeah.
Are you re-engineering your data model at that point, or what are the mechanics of doing that? Because I'm assuming the monolithic database is not really in the physical structure that you want it in. Or the model is not what you want, right? So how do you do that, or what?
Yeah, that's great. No, that's a great question. Yeah, I mean, part of the this margin is too large to contain the proof. Proof is left to the reader kind of thing here is, yeah, you have to figure out a way to cut away. You have to find a seam. So I'll give you the third, so for every question gets a reference. The third reference that I will leave you with is a fantastic book by Michael Feathers called Dealing Effectively with Legacy Code. I worked at Google. There was exactly one book that was required reading for new people to join Google. It was this book, Michael Feathers, Dealing Effectively with Legacy Code. So I'm going to use his terminology because he's awesome. You try to find a seam, just like a seam in clothing, right? And sometimes that seam exists. Your point of your question is, wow, that seam doesn't, I wish that seam existed. I wish I could take this, arm of the sweater off easily, but nope, there's no seam there. So you got to create it. And sometimes that's almost almost often, in a big legacy spaghetti situation that's lived for a long time, which like probably actually runs and makes a lot of money and is important, you have to create, sometimes you have to create those seams. Does that make sense? Yeah, it's a great question. Yeah, please.
When you're talking about data, one of the things that comes up a fair amount is the analytics side of data.
Yes.
So we're used to having the ability to go in and do not necessarily ad hoc, but potentially ad hoc spur of the moment. So like I want to go look at my data for analysis.
Totally.
The approaches that you're describing are approaches that have a fair amount of effort involved in stitching data back together.
Yeah.
Are there patterns that you're aware of for putting stuff back together that don't have as much effort involved? Because when you're looking at it from the standpoint of, okay, well, I've been operating it, now I want to understand what it's doing. Now I want to understand how my business is performing, all those things.
Yeah, that's a great question. Thank you for that. I mean, the answer is an analytic system does stitch it all back together. So the analytic system is, in some sense, like a reification of the monolithic approach to data. Like, it doesn't work but it has a different set of ilities. It has a different set of ilities when you're in an analytic situation. And so at Stitch Fix, the operational systems work like this, where when we are done with this migration, this re-architecture, we're going to have lots of different services, each with their own database, and nothing shared. And then the data scientists will actually, as they do today, they ETL data out of our sort of service databases, and they put it back together, and I like to say Hadoop on it. So like they will do a bunch of MapReduce computation on that data. It doesn't mean they have to put the entire monolith back together, because if one of the data scientists is doing the styling algorithm, like she actually doesn't care about the warehouse stuff. Does it make sense? Like but analytic systems in general do put back together all this disparate stuff. So that's actually a legitimate thing. Please.
So speaking of banks, and banks needing lots of regulation, and so then business rules changing all the time, that means your data needs to change all the time. And systems we could buy or rent now come with admin screens to add attributes, here and there and everywhere. But the systems we build tend to be hand-carved rows and columns, or not as easy to change. So I'm looking to see if there's companion strategies around configurable data that play nice with all the rest of this.
Yeah, sure. It's an excellent question. It's an excellent question. It's orthogonal to all the things I'm talking about. So let me say it this way. All the techniques you might want to use around making your data configurable, you can also do in a world like this. Does it make sense? You can also, the trick is, how do you get an interface that is sufficiently configurable to be interesting and flexible, but not so flexible that it is unmeaningful? Does it make sense? No. A little bit? And I appreciate that is architectural hand-waving. I mean, in a particular context, I think we could talk about, like, what's the right scope or data responsibility for a particular thing. But yeah, there's always this tension, whether we're talking about microservices or monoliths or databases or whatever, there's always this tension between flexibility and kind of my being able to reason about it, if that makes sense. I mean, like, we could make it's easy to design the perfectly flexible data model, but it's also useless. I mean, you're not suggesting otherwise, but.
An early experience was using SGML to store product model information into tables, right? They weren't going to get big, they'd fit just fine.
Yeah, totally.
And so then XML as an interface language was intentionally to be flexible.
Yeah, so you're describing a data-driven interface.
Right.
Yeah.
But then we say, well, our rules are, all the SOAP data will be validated at all the interfaces, and so now you poured concrete around your service interfaces, and now it gets much harder to change unless you think about that ahead of time.
I agree.
Yeah. So next year's talk will be data and services with lots of flexibility.
It's been a while, but once upon a time, I have worked in systems that are more like that. So as a very broad brush generalization, consumery systems tend to not have super rich data by comparison to enterprisey systems, but they tend to be like really fast reads and writes, whereas, I mean no disrespect, like enterprisey systems like you're describing are like, it's not super fast, but like, wow, that data model is really complicated and really interrelated. Yeah, like, you have to think about that. But they are not infinitely interrelated. Does it make sense? Like like when we go for, if you decide, like reference the first third of the talk, if microservices look like the right solution to the problems that you currently have, then we do need to think about some way of breaking down your domain via domain-driven design, or some like domain way of decomposing it in a way that where each like unit is a service. And yeah, there is often a tension, like you say, between this structure that I can reason about and flexibility of it. Yeah, I get it. I agree with you.
Yeah, and I think the hint, and I'll stop with that, was that consumer-facing systems, simple, scale very far, very fast. Enterprise back-office systems, maybe lots of complex data, and be careful. Yeah.
True. And also, yeah, and also, I mean, I don't want anybody to get, if we decide that for the particular problems that a particular back office system you're thinking about has, if microservices feel like a solution to that, you can solve those problems with a microservices approach. How do I know that? Amazon has done it, Google has done it, Netflix has done it. Like, it's doable. If microservices aren't the solution to your problem, like, don't use them. Does that make sense? Cool.
All right, we have to.
All right. Thank you.
We have to thank Randy.
That was really great.